Hello and welcome to Suggested Problem Set 1.2, Part 2. So we have an antelope moving with a constant acceleration that covers a distance between 2 points 70 meters apart in 6 seconds. Its speed as it passes the second point is 15 meters per second. And so we're looking for speed at the first point and acceleration. So if we want to think about this graphically for a second, we have an antelope moving with constant acceleration covering a distance between 2 points. So let's call the first point just 0, 0, and we'll say our second point is 70 meters apart. So if I look at just a quick sketch of a graph here, as long as acceleration is constant, I should have a parabolic position time curve, with this being, a 6, not a 7, 6 seconds later, at a position of 70 meters. So the velocity graph, if I want to think about it, should look something like this. Now I don't know for sure if it starts from rest, but I do know that at 6 seconds it should have a velocity of 15 meters per second. So I'm looking for a few things here. So I have a distance, rather a displacement, which is 70 meters. I have a time, which is 6 seconds. I have an unknown acceleration. And I have a known final velocity. So I will also go ahead and point out that I have an unknown initial velocity. So out of these 4 things, I want to start off by finding the speed at the first point. So I would like to find v naught. So there's a few ways I can do this. One is I can look at my kinematic equations, and I can try and figure out which equation has my unknown variable. So for part A, I'm looking for v naught. So I want an equation that involves delta x, time, v, and v naught. So do I have any equations that involve these? Well, hopefully I can think about this a few different ways. I can think of it as, for instance, average velocity. So average velocity, or delta v, is equal to delta x over t. And if I rearrange this, I will see that this is a very simple v minus v naught, which is equal to delta x over t, I'll just call. And then if I'm looking for v naught, little rearrangement gives me v, my bad. Pardon me, hold on a second here. I gotta do this the hard way. Will give me v plus delta x over t. So, I'm sorry, v minus, forgive me. So, v naught will be 15 meters per second minus, in this case, 70 meters over 6 seconds. And so, calculator yields an initial speed of 3.3 repeating, too many periods, 3.3 repeating meters per second. Part B asks me to find, if I scroll up, asks me to find the acceleration. So now I'm looking for acceleration. So I can do this a couple ways. I can do it based off of my original information, which if I'm unsure about my answer for A is not the worst idea. So I have delta x, time, final velocity, and acceleration. So, how do I put all of these together? Well, there's a few different ways to do it. I think the easiest way to do it actually is to use the v naught that I have. So if I use v naught, I can actually look at acceleration being defined as change in velocity over time. So that will be v minus v naught over t. And since I have v final as 15 meters per second and v naught as 3.3 repeating all over my time period of 6 seconds, my acceleration should work out to be 1.94 meters per second squared. So this is just using simple definitions of average velocity and average acceleration. Question 2.21 says the fastest measured pitched baseball left the pitcher's hand at 45 meters per second at a speed of 45 meters per second. And the pitcher was in contact with the ball over a distance of 1.5 meters, and there was some constant acceleration. So there's a few assumptions that need to be made here. Number one is that the 45 meters per second is a final velocity. Hopefully, if you're throwing or pitching a ball, your initial velocity would be 0 because you're just holding it. So I also have a distance of 1.5 meters. I'll just call that my displacement or my delta x. And then I have some unknown acceleration. So I have v, v naught, delta x, and a. So now comes the time when I need to use one of my kinematic equations. So if I have all of these pieces, I would like to use the kinematic equation that involves all 4 pieces. V equals v naught squared plus 2a delta x. And in this case, I will be solving for acceleration. So I'm going to do that prior to substituting. So I'm going to have v squared minus v naught squared equals 2a delta x. And then I'm going to have dividing through by 2 delta x and putting acceleration on the left, v squared minus v naught squared divided by 2 delta x. So now I can substitute values. So I have 45 meters per second squared, or meters per second, and then squared, minus 0 squared over 2 times 1.5 meters. And so, of course, this is meters per second squared over meters, which if we want to do all of this out, meters squared over second squared over meters. So one of my meters cancels and leaves me with meters per second squared. Putting this into a calculator, I get an acceleration of, I'm going to double check this because I don't believe it completely. Of 675 meters per second squared, which is an insane amount of acceleration, considering 1g of acceleration is about 10 meters per second squared. Then B asks for how much time it took for him to pitch it. So I have acceleration, I have all of these different terms, and I want to find time. So one of my equations is very easy to do for this, and that is v equals v naught plus at, which is our first kinematic equation. So so I will be solving for time. So I can actually rearrange this fairly simply. V minus v naught equals at. Therefore, time in this case is v minus v naught over acceleration. So substituting here, I would have 45 meters per second minus 0 over this acceleration I found to be 675 meters per second squared. So plugging this into a calculator gives me a very, very quick time of 0.0667 seconds. And again, I'm basically going to be using 3 significant figures most of the time. All right, number 2.24. So a pilot that accelerates at more than 4g begins to gray out, which is not a good thing for a pilot. So assuming constant acceleration, what is the shortest time that a jet pilot could start from rest and get to Mach 4, which is 4 times the speed of sound? So I'm going to look down here and I see that the speed of sound is actually given. So let's pull out some information from this problem before we get started. The first bit is that my acceleration maximum is 4g. So hopefully we recall that 4g's is going to be 4 times 9.8 meters per second, or, if you have a calculator, a nice 39.2 meters per second squared. Second part is Mach 4. So I'm actually going to start from rest to get to Mach 4. So v naught is 0. V final is going to be Mach 4. Well, that's going to be interesting. So that's 4 times the speed of sound, which is 4 times 331 meters per second, or, with a little bit of calculator magic, 1,324 meters per second. And the last bit is the shortest time, so I'm looking for a t here. So I have acceleration, v naught, v final, and t. I have an equation that involves all three of these. That is kinematic equation number 1. So I have v equals v naught plus at, and I'm going to solve this for time. So, little rearranging, oops, that is not a v. Little rearranging gives us v minus v naught over a is equal to t. So substitution will be 1324 minus 0 over 39.2 meters per second. And with calculator, this gives me a time of 33.8 seconds. So again, I'm using 3 significant figures here. So that is the shortest time that I can go to Mach 4 without graying out. Now part B says, how far does it travel during this period of acceleration? So I can do this 2 ways. I could either use the second kinematic equation or the first kinematic equation, but I'm going to go and use the first kinematic equation, or second, sorry. So delta x is equal to v naught t plus 1/2 at squared, since I have a time. So delta x is my displacement. My initial velocity is 0, so that just leaves me 1/2 times my acceleration, which is calculated to be 39.2 meters per second, times the square of my time, which is approximately 33.8 seconds squared. So the displacement that my plane travels in this time is approximately 22,400, if I want to use significant figures, and that is in meters. So again, 3 significant figures pretty much throughout the entire set of problems here. Question 2.32 looks similar to the one that we did in class. I have 2 cars, A and B, moving along the x-axis, and the positions of those are given in this graph here. So in motion diagrams, now we've not seen motion diagrams before. We want to show the position, velocity, and acceleration of each of these cars at 3 different time intervals. So this is a little interesting, but I will go ahead and do this. So a motion diagram is essentially just a series of dots, like snapshots, taken at different points in time. So we'll start with B as a motion diagram, and then we'll do A. So we can see that B has a constant velocity. I can see that from this constant slope. And what's happening then is that at different instants in time, my car will have traveled the same distance. So you can see each of these dots is approximately the same distance away. So you can think of this as t equals 0, and this as t equals 3 seconds later. So the A car, by comparison, will start ahead of the B car. So I will start somewhere slightly to the right. And then I will see that the A car actually needs to be about the same position as B at the 1 second mark. And then my A car is behind my B car for a moment. And then at the 3 second mark, they are again equal. So let's see here. So a little behind the B, and then at this one they are equal. So B says, at what times do they have the same position? Well, I can see that that is when these 2 lines intersect. So at approximately t equals 1 second, and approximately, we'll say t equals 3 seconds. The second part, now we're on C. We want to graph velocity versus time for these 2 cars. So I can just do a quick sketch here. It does not need to be perfect, but it is velocity over time. And so my velocity for the A car is a little more difficult than B, so we'll start with B, and we'll do this in 2 different colors. So we'll say that graph B, which is light blue, has a constant positive velocity. So we'll start with a constant positive velocity. Then the A car, which is either pink or red, I'm just going to go with red, starts at a near zero velocity and increases from there. So it's going to be something like this, where it ends up with a final velocity higher than that of car B. So I'm actually going to make this a little more pronounced, something to that effect. Then D says, at what times do they have the same velocity? So D would be when these two intersect. So if I look at my graph, the implication is that these will have the same velocity when their slopes are equal. So a tangent line, if I look very closely, if I were to draw a tangent line about at 2, that would be when the tangent line would be parallel to graph or line B. So I would say that approximately at t equals 2 seconds is when these cars have the same velocity. E asks, when does car A pass car B? So I want car A to pass car B, which is a little interesting. So what does that mean? First off, they have to have the same position in order to be passing, and then car A must be moving ahead of B. So the only time when that occurs is up here at t equals 3 seconds. And the second, or part F really, is when does car B pass car A? And that is down here at t equals 1 second. So you can see that these are essentially just different ways to interpret motion graphs of multiple objects. Question 2.33 says a small block has a constant acceleration as it slides down an incline. So this will be the first of many blocks that we draw on an incline. So the block is released from rest at the top of the incline, and its speed after it has traveled 6.8 meters to the bottom is given. What is the speed when it is a certain other distance from the top of the incline? So this is an interesting question. So I can go at this a few ways. So I'll start and I'll just try to pull information out of the problem. So I have a delta x of 6.0 meters. I know I'm released from rest, so v naught is 0. I know that at the bottom of the incline, my speed is 3.8 meters per second. I don't know anything about time. And I want to know what is the speed when it is 3.4 meters. So some other delta x later is 3.4 meters. So I'm going to use this information here to find acceleration, because I can kind of see that there's no time involved, and I know that the only kinematic equation applicable when there's no time is the third, which is v squared equals v naught squared plus 2a delta x. So I'm going to rearrange this and solve for acceleration. So acceleration will be v squared minus v naught squared over 2 delta x. And since our v naught is 0, that makes this a little easier. So acceleration will be 3.8 squared minus 0, go ahead and write that, over 2 times 6.8. So my acceleration for this cart will be a nice, or not nice rather, a nice 1.062 meters per second. So I'm not rounding this one much because I want to use it as long as a number as possible until the very end. So the speed when it's 3.4 meters from the top is going to be the same thing. We're going to use the same equation, but instead of plugging in all of these numbers, including a final velocity, I'm going to find the final velocity. So v will be the square root of v naught squared plus 2a delta x. Again, I'm solving algebraically before I substitute to cut down on transcription errors. So this will be the square root of 0 plus 2 times 1.062 times now 3.4 meters. And I will see that my velocity ends up being 2.69 meters per second. Now question 2.61 says a gazelle is running in a straight line along the x-axis, and the graph here shows this animal's velocity as a function of time. During this first 12 seconds, I want to find the total distance moved and the displacement of the gazelle. So if I look at this graph really quickly, I can see that all of the velocity is in the positive direction. So for A and B, I'm actually going to cheat and say that distance is equal to displacement here. I know that, again, because all velocities are greater than 0. So there is no time when I'm traveling in the negative direction. So how do I find this displacement and distance? I'm going to find the area beneath this graph. So I can cut it into some smaller chunks in order to make that easier. So first I'll start with a little rectangle here, and then I'll cut this into a triangle, and then I have another triangle right here on the side. So this first rectangle has a base of 10 and a height of 4. This triangle up top has a height of 12 minus 4, which is 8, and again a base of 10. And then this entire triangle on the right, hopefully this is legible, has a height of 12 and a base of 2. So my area, or my displacement, so I'll say A and B here, just be delta x, is going to be 4 times 10 plus 1/2 10 times 12 plus 1/2 2 times, I'm sorry, I messed this up. This 12 should be an 8. And this is 1/2 2 times 12. So my displacement / my distance for this particular problem will be, after a little calculator magic, 92 meters. So C says sketch an acceleration graph showing this gazelle's acceleration. So I'm going to look at my graph and I'm going to sketch the acceleration, which is just the slope of my velocity graph. So if I look at this, I can tell the slope pretty easily for the first section. So I go up by 8 in a time of 10. And actually I'm realizing I'm going to want a negative value at some point. So I have a negative and a positive. So my positive part will have a value of 0.8 for 10 seconds. So this is the 10-second mark. And then for the final 2 seconds, I'm going to have a slope of negative 12 divided by 2, which is negative 6. So that is quite a negative value, but I'll just draw it not to scale. And this is all I have. That's all you need.